So we're going to briefly look at anhydrides. This comes up on the AP test here and there every once in a while, and they're super easy. So this way you know what to do when you see them. Okay, so I want to point out that we can predict some things. A metallic oxide is often called a basic anhydride. So catch that anhydride, hydride with water and not water. So a metal oxide is lacking the water that would be necessary to make it a base. And I want to show you graphically how this is going to look. So I'm going to grab my annotation here. And so Na2O, let's break that into kind of just a quick little structural drawing. It's not this, but I want you to see what happens. Okay. We bring in water, and water is going to be attracted hydrogen to oxygen there. So a bond's going to form there, and what do we get? We get one NaOH out of what I've circled, and what is left over is a second NaOH, and that's why it gives us two NaOHs when you balance it. You know what water is. Water's got to be H2O. Sodium oxide, oxygen's a -2, sodium's a +1. We did a crisscross there, okay? So I'm not breaking any rules when I'm talking about the pictures that I'm going to be drawing. And they're not official Lewis structures or things like that, okay? That's ionic. It really needs to have the brackets and charges, and that doesn't matter. I just want to show you for the test something quick that you can do in order to get the answer and move on. So on the next, nope, sorry. I wanted to clear that and I then marked it up again. Okay. Next we have non-metallic oxides and I want to do the same thing. Okay. So non-metallic oxides are acidic anhydrides. So catch that. Metallic oxides and water give you a base. Non-metallic oxides and water give you an acid. That is well worth memorizing. It's just a little nugget to stick in your head, and you might get some test questions correct with that. I want to draw this again, and watch how I'm going to do this. I'm going to draw sulfur with its three oxygens like that, okay? And I'm going to draw hydrogen. Let's see, water. I'm going to draw water like this because I want you to see what's going to happen. This is where that bond's going to form. When that bond forms, what do we get? And yeah, if you actually look this up, there's supposed to be some double bonds some places. And again, these aren't official. I just want to give you an idea of how to do this easily. Okay. I'm just putting the two pictures together. What do I get when I put the two pictures together? Here's my SO4 and here's my H2 and I get H2SO4. And we know what water is, okay? And so we've got a balance, and sulfur trioxide, like the prefixes tell you what it's going to be. So it's just a matter of getting it to balance. I will tell you this, the oxidation number of the sulfur is going to stay the same. So if oxygen's a -2 and I've got three of them, sulfur's a +6. So sulfur still has to be a +6 here. Oxygen is still a -2, and that gives us -8. And that's why we have two individual hydrogens. So it works out the same way in all regards. Doing crisscrosses, looking at your oxidation numbers, balancing your reaction, and doing my quick little drawings all give you the same result. So I want you to see that you actually could do just quick little drawings, get your answer, and move on, and not worry so much about all of the oxidation numbers and things like that. Okay, let's do some practice. And I am going to go fast because I know how this works. And you can watch this video over and over again if you need to see it. Now, first off, I want to write the acid or the base. So I need to, these are anhydrides. How do I know they're anhydrides? They don't have water. So I'm going to be adding water to each and every one of these. Okay. And certainly equilibrium arrows, because we have now discussed equilibrium, but you know, don't worry about that so much. That's probably not at all what they're going to be asking on the test. Okay. What did I say previously? Basic, sorry, let me start again. I'm flipping it. Metallic oxides are going to give you a base. Non-metallic oxides are going to give you an acid. So since carbon is a nonmetal, I have a non-metallic oxide. This is going to give me an acid. All acids start with H. And I don't know why my other PowerPoint decided to just randomly show up in the background. Sorry about that. Give me a moment. I'm just going to do a little bit of this, and we'll be good to go. Okay. So anyway, PowerPoint doing random stuff, whatever, is what is. Okay, so I need to actually start over on my annotations because they don't match up. Here we go. So I'm going to add water, and I'm going to smush this all together to make an acid. All acids start with H. Okay. Now, look, I have two H's, I have one C, and I have three O's to work with. Is carbonate ion a thing? Yes, it is. So there we go. I'm done. That easy. Okay, I'm going to add water. Now, this is a metal oxide. It's going to give me a base. And so I'm going to have, okay, bases end in hydroxide. If you don't know that, we have covered that. You need to know that. Arrhenius definition of acids and bases. Acids start with hydrogen, bases end in hydroxide. It's always going to be the metal that's going to be starting your base. And it's always going to have the same oxidation number it did before. Now, lithium only has one. So lithium hydroxide has to be my base, and I am not balanced as I look at that. So I'm going to put 2 there, and now I'm balanced. Okay, just that easy. The other way, I could have done the drawing. And if you like drawings, good news, you can always do the drawings. And then I'm going to do some groupings. There's one LiOH. Here's the second LiOH. And then I would know it's 2 LiOH, and I'm done. Okay. What about this? Well, so we look up selenium. It's a non-metal. So I have to make an acid. I'm going to start with H. Okay. And I'm going to put together what I have here. H2SeO4. Okay. Is this a thing? Yes, it is a thing. It's not a common polyatomic ion, but selenate ion is an ion and it has a -2 charge. And so it all works out and I'm balanced and I'm done. There we go. Okay. And this is a metal oxide, so it's going to make a base. It starts with a metal and it ends in hydroxide. This is not going to be crisscrossed correctly because calcium's a +2, right? So I'm going to do that. Now I check if I'm balanced. Yes, I am balanced, and that's it. So let me do a quick little drawing here. Ca started with 1O. I'm going to add an H from hydroxide, from the water. Here is one hydroxide. Here's the second hydroxide, all stuck together with that Ca. Okay. So whether you look at oxidation numbers and crisscross, whether you just balance, smush together what you have in balance, or whether you use a drawing, it all gets you to the same place. So this one might be tricky. We're going to make an acid. So acids start with H. I'm going to have some N and some O of some sort. Okay. So now here's the thing. The oxidation number stays the same. So nitrogen was a 5. So it's got to remain a 5. And if nitrogen is a 5 and oxygen is a 2, I'm going to need 3 of those because I also have a +1 here, right? So you see how I have a +6 and now I have a -6. So there we go. So it's HNO3, nitric acid. And there we go. Also, years ago, I was told it could be, if it's the high oxidation state, because nitrogen can be 3 or 5. If it's the high state, it always ends up the 8, which is always true. And if it's the lower charge, it ends up the ite, which is true. So there we go. Okay, now we're going to go opposite with these. So I'm not going to spend much time with these. These are all acids, so we're going to write the anhydride. So first thing I'm going to do on each is I'm going to pull out a water. And I'm just going to check after I pull out the water, is the leftovers like correct? So if I pull out two H's and one O, is SO3 a thing? Yes, sulfur trioxide's a thing. I'm done. If I pull out two H's and one O, could carbon dioxide be a thing? Absolutely, it's a thing. So there we go. If I pull out two H's and one O, is sulfur dioxide a thing? Yes, it is. If I pull out two H's and one O, I get HPO3. That's not looking like what I'm looking for. So I'm going to need to like balance this. I'm going to need to pull out more water. I'm going to pull out two waters, okay? So I'm going to erase what I previously had. I'm just going to clear all the drawings real fast. I'm going to pull out two waters here and see what happens, okay? If I pull out two waters, I'm pulling out, oh, this isn't going to be fun. I'm going to need another H3O PO4 to pull out two waters. Okay. And then what would I be left with? Something that's not fun. Okay, so I'm going to pull out three waters. I'm going to pull out three waters. Okay. So I have two H3PO4s. I'm just going to put the coefficient 2 there now. Okay. I'm not going to have it written twice. I'm going to put the coefficient 2 there. And what am I left with? Now look at this. See, so I'm pulling out 6 hydrogens. So I'm pulling out 6 hydrogens. And I'm pulling out 3 oxygens. 2 times 4. Okay, 2 times 4. Well, let's go with the phosphorus first. Two phosphoruses. Okay. And then 2 times 4 is 8, but I'm pulling out 3 oxygens. So 8 minus 3 is 5. And P2O5 is a thing. Okay. What could I have done otherwise? That's kind of me looking at the drawings. All right. What could I have done otherwise? I absolutely could have done this. I could have said H3PO4, arrow water, plus P and O of some sort. And I know O must be -2. Now the phosphorus has to keep its oxidation state. It here in PO4 is being a +5, so it has to be a +5 here. So I would crisscross. And then I would balance. And I see I need a 2 there for the 2 P's, and I need 3 there for the 6 H's, and now I'm balanced, and there I am at the same place. So that's what I want to show you, is simply that no matter which way you view it, we get the same thing. Okay. So you can view it as structures with drawings. You can view it as what if I look at just what I have, and you can view it as in terms of keeping the oxidation numbers the same. Okay. What if I pull out, oh, I can't even pull out a water from that as it is, right? Right? Okay. So let's do a quick little drawing just over here on the side. Here we go. Quick little drawing. HNO2. Let me grab another HNO. Can I pull out one water from those? Yes, I can. If I pull out an H2O, gets rid of that H, and one of the O's. What do I have left over? N2O3. Is N2O3 a thing? Absolutely. Dinitrogen trioxide's a thing. I'm done. Okay. What did it take to get there? 2 HNO2s, 1 water, and 1 N. So again, you can look at oxidation numbers. You can look at just mashing and pulling apart the formulas themselves and seeing what you have. And you can look at the oxidation numbers. The nitrogen started as a 3 over an HNO2. Prove it to yourself. And it remains a 3 over, wow, I'm sorry, I wrote a 5. That should have been a 3. I hope you were yelling at the screen that I did it wrong. Yeah. So that I think I just looked above and transposed the 5. That should be N2O3. There we go. That's what we decided. Okay, and now we're going to do the same here. So these are bases. I'm going to pull out a water and I'm going to make a metal hydroxide. So that's one way to view it. Just be like, what's my metal? Sodium. What's my oxide? Well, oxides are oxygen, and do a crisscross and then go through and balance. Okay, that's one way to view it. Absolutely. Not a wrong way to view it. Okay. The other way to do it is like if I pull out two H's, that gets rid of that. And one O, what do I have left over? I have Mg with one O left over. There we go. It's all balanced. That's what I've done. What's another way to do it? Let's draw it out. I have Fe with an OH there and an OH there. That's why it's, FeOH2. And I'm going to make a water. So let me get rid of that. Let me get rid of that. Let me get rid of, well, I I got rid of the wrong thing. Can I undo that? Yes, I can. There we go. Okay. I get rid of that. There's my water. Okay, those three things I scribbled out are my water. What's left over? FeO. And there we go. Okay. And so we can do it that way. So there's like really three different ways. Pick the way that's easiest for you. Um, since I'm well versed in all three ways, they're all equal in my mind, and they truly are. They're all going to get you the same place. Let's do this. Let's just do formulas based again. I know I'm going to make water, and I need to make a metal oxide. Aluminum's always a +3, oxygen's always a -2, so I'm going to crisscross. Now I need to check if, okay, now be careful. If you do it that way with the oxidation numbers, you got to check if it's balanced. It's not balanced. I need a 2 there. And then I'm going to need a 3 there. And then I believe I'm balanced. And so there I go. Okay. So that's all there is to these. Super quick. May get you a point or two on the test. And every point is precious, especially when it's something that you could do three different ways. You could do it with a drawing if you just want to take a mental break from numbers and letters and do some drawings. Cool. You could do it with the oxidation numbers, being sure you maintain the oxidation number of the metal and the non-metal the same, and then do crisscrosses and balance. And you can just kind of like cross out as you go and show what's left. And it should work all three ways. All right, so that is how we handle anhydrides. Good luck.